Hello everyone, welcome to our third session on formation of PDE by elimination of arbitrary constants. In the last video, we saw some examples to form a PDE by eliminating the arbitrary constants. So which is the continuation of our previous session. So in this also we are going to see some problems for the formation of PDE by eliminating the arbitrary constants. So this is our next example here. We have our equation as log of az minus 1 is equal to x plus ay plus b. So let us consider given equation as 1. Now differentiating 1 partially with respect to x and y, we get two more equations that are, when you differentiate this with respect to x, you get 1 by az minus 1. When we come to the variable term, this az comes as a into dou z by dou x. Since we know that dou z by dou x can be taken as p, I'm writing this as a into p, which is equal to the right hand side that x becomes 1 when you differentiate it with respect to x partially, and this is treated as a constant, so the remaining two terms are becoming 0. Similarly, with respect to y, when you differentiate, you get 1 by az minus 1 into a into dou z by dou y, that is nothing but q. So which is equal to, here x becomes 0, here when you differentiate this with respect to y, you get a. So from this we get ap is equal to az minus 1, and from the next equation we get aq is equal to a into az minus 1. We can cancel this a out, and from this we get q is equal to az minus 1. So if we can give a substitution for this a, we'll be getting a partial differential equation. So how can we get the substitution for a? From this we can write a as what? A is minus 1 by p. But this a is minus 1 is nothing but q. So we can write this a as q by p. So now using this substitution here, we are getting our resultant PDE, which is nothing but QZ by P minus 1. So upon simplification, you can write this as P into Q plus 1 is equal to QZ. So this is what our resultant partial differential equation. See our next problem. Here we have our equation as x square by a square plus y square by b square plus z square by c square is equal to 1. In this equation we have three arbitrary constants. As I said already, if the given equation involves the number of arbitrary constants, which is the same as the number of independent variables, the resultant PD will be of first order. Suppose if the number of arbitrary constants is more than the number of independent variables, then the resultant PD will be of 2 or higher order. So here also we are going to get a second order PDE while forming your PDE by eliminating these three arbitrary constants. So now let us take, this is our first equation. So I'm going to differentiate this partially with respect to x now, so that I'm getting 2x by a square plus this becomes 0. This is, since that is also a function of x and y, while differentiating it with respect to x, I'm getting 2z by c square into dou z by dou x. That is nothing but p. And in the right hand side, it becomes 0. Similarly, differentiating the same with respect to y, I'm getting 2y by b square plus 2z by c square into dou z by dou y, which is nothing but q. From this, I'm getting this equation. Okay, since the given equation involves three arbitrary constants, we are going for the next differentiation. I'm going to differentiate the first equation again with respect to x. This implies that I'm getting 2 by a square plus here 2 by c square. Here I have to follow the UV rule. because I'm having two functions in product. So keeping this z fixed and differentiating this p, I'm getting that is p is nothing but dou z by dou x. So dou by dou x of dou z by dou x is nothing but dou square z by dou x square. And keeping this p fixed, differentiating z, I'm getting dou z by dou x, which is nothing but p again. So this comes as p square, which is equal to 0. Similarly, differentiating the second one with respect to y, what I'm getting? 2 by b square plus 2 by c square, and here it is going to be z into dou square z by dou y square, plus this one is going to be q square. Okay. Now I'm going to differentiate the first equation, that is not the first one, the second equation with respect to y again. So differentiation of this with respect to y, what I'll be getting, the first term becomes 0. Okay, and here it is 2 by c square, 2 by c square, and here I'm going to differentiate this with respect to y, which means z into keeping this z fixed and differentiating this dou z by dou x, and with respect to dou by dou y, I'm getting dou square z by dou square z by dou y dou x, plus here keeping this fixed p and differentiating z with respect to y, I'm getting dou z by dou y, which is nothing but q. So this is what I'm getting if you differentiate the second equation with respect to y. So here I will differentiate with respect to y. Here it is what? 2 with respect to x, and this one is 3 with respect to y. So from this, by using the above equations, I can eliminate the arbitrary constants. That is, how can I write this equation? Here you see, from this actually there is no constant involved in the last equation, which means what? We have got our resultant PD. That is what? From this, there is, since there is no arbitrary constant involved, because this is nothing but z into dou square z by dou y dou x plus PQ is equal to 0. So when you take this product term to the right hand side, the equation involves no arbitrary constant. So this can be considered our resultant PDE. I hope you understand this video. Thank you for your patience.